And so half-life is a concept that you probably are very familiar with, something that you've studied in first-year chemistry, something you've studied in earth science. It is the time required for half the mass to decay. So we're talking about radioactive isotopes. The nucleus is breaking down, and over time there's less and less of the substance than what you started with. In other words, it is the time it takes to go from 100% of the mass down to 50% of the mass. So we're going to take a look at an example here. We have iodine, and it is decaying. It starts at 16,000, and then it's decaying over time. Eventually, it gets lower and lower and lower and lower. But quite interesting, it should never reach zero because there's always going to be some amount of it left over. There's nothing that you can divide by 2 to reach zero. So it's going to get really, really small in the end. But technically, there's still some left at the very end. And there'll always be some left over. So part A, determine the half-life, abbreviation T1/2, of iodine-131 using the graph above. So if we start off at 16,000, exactly 1/2 of 16,000 is going to be 8,000. So the amount of time it takes to go from 16 down to 8 is going to be the half-life. So from 0 days to 8 days, that's the half-life of this substance. And I can check that again. If I start off with 8,000, after one half-life, I would expect 4,000 left. And this tells me it would take also 8 days to achieve, because we're starting here at 8 days and ending at 16 days. That's the difference of 8 days. Just like before, it was 8 days for that half-life. I'm going to repeat that. If we're now at 4,000, how long does it take to reach 2,000? So at 16 days, you end at 24 days. Again, another 8 days has passed. So something interesting here, our half-life is consistently 8 days. And in this class, the half-lives of the substances that we study will always be consistent, meaning that the reactants or the compounds that we study in terms of half-life are always going to be first-order reactants. First-order reactants have consistent, constant half-lives. So if we're asked what is the order of this this radioactive isotope, it is going to be first order because it has a constant half-life of 8 days. Every single time is 8 days. If it was zero order or second order, the half-lives are not constant, but in this class we are only concerning ourselves with constant half-lives, so therefore we're only looking at first order reactants with regards to half-lives. So how can we use this to graph our data here? We have time on the x-axis, and now they want us to label the vertical axis. Have a straight line. I have to think back to the graphs for 0, first, and second order. They're telling me this reaction is first order, and we have a straight line, so it must be the natural log of the concentration of iodine plotted here on the y-axis. Okay, because I know natural log of concentration is what's going to give me that straight line. Part 2, what are the units of the rate constant for this decay? Well, if it is first order, then I know that it's just going to be 1 over the unit of time of days. Because I know the shortcut for units on K, it's 1 over the molarity raised to the power of overall minus 1. But since our overall order is 1, it's 1 minus 1, and that gives me 0. So it's just going to be 1 over days. Part 3, explain how the half-life of iodine-131 can be calculated using the slope of the line plotted on the graph. So if I have this graph, natural log of iodine, on the y-axis versus time, I remember that K, your rate constant, is the absolute value of the slope of the line in natural log of iodine versus time. Okay, so if I have the graph with a straight line, I know K is going to be the absolute value of that slope. And there is another way that we can calculate half-life, and it's going to be equal to natural log of 2 over that rate constant. And this is a formula given to you on your formula sheet. This is half-life is equal to natural log of 2 over baby K, the rate constant. So if you know the half-life is 8, you can plug in 8 into this equation for half-life and then solve for K. You're going to see it written most likely like this. The natural log of 2 is 693 over K. Okay, so I believe it's this one that's on your formula sheet. But sometimes it's hard for us to remember the 0.693. So I like to think of it as natural log of 2. That's something I can remember a little bit better. Okay, so a couple things to note. K, your rate constant, is the slope, the absolute value of the slope of the line. But if you don't have this graph with the slope, you can use this formula and plug in the half-life and solve for K. Likewise, if you know the rate constant and they ask you for half-life, you plug in K and solve for T1/2. Part C, compare the value of the half-life at iodine 131 at 25 degrees Celsius to that at 50 degrees Celsius. Half-life is constant. It is independent of temperature. Half-life is independent of temperature, meaning it doesn't change when temperature changes. So the half-life at 25 degrees Celsius is the same at 50 degrees Celsius.